Let's look at the insertion into a maximum heap. We still have a binary tree here, but before we look at the insertion operation, let's look at the binary tree first and determine if it is a maximum heap or not. The first property of the maximum heap is that it is a complete binary tree, and the value of each node is greater than or equal to the value of its children. So first of all, we need to determine if it is a complete binary tree or not. We can see that we have a binary tree and it has its nodes placed from top to bottom, left to right. And we have empty space here because we don't have enough nodes, so this is also a complete binary tree. And we can also see that the value of each node is larger than the value of each child node, so it follows from our current binary tree is indeed a maximum heap. Now we are looking at inserting a node 15 into the maximum heap. After we perform the insertion into the maximum heap, we have to check that if the resulting tree is still a complete binary tree. The position of 15 can only be the right child of the node 5, and when we put 15 on the right child of the node 5, you can see that 5 is smaller than the right child 15. But one property of the maximum heap is that each node must have a value larger or equal in the value of its children. So what should we do here? All we have to do is swap 5 and 15. When 5 and 15 have been exchanged, you can find that our node 10 is smaller than the left child 15, so it still doesn't meet the properties of the maximum heap. Now we need to exchange 10 and 15, and when this exchange with 10 and 15 is done, at this point, if we look at our binary tree, we will find that it is a complete binary tree and that the value of each node is greater than that of its children. Now we had insert 15 into our original maximum heap, and we have constructed a new maximum heap which completes the insertion of the maximum heap. Now let's define add method, which is responsible for adding a new element to the heap while maintaining the heap property. And then we increment the real size attribute by 1. This is because a new element is being added to the heap, so the number of elements in the heap will increment by 1. So this is essential for keeping track of the current number of the elements in the heap, where it helps us to manage a capability of the maximum heap and ensure that the maximum heap property is maintained after we add in new elements. And then we check if the number of the element in the heap has exceeded the maximum allowed heap size. If the condition is met, we just print the message added too much element and decrement the real size by 1, and then returns without adding new element to the heap. This check helps us to ensure that the heap does not grow beyond its allocated size, which can prevent any potential issue with memory allocation or data management. And when we're working with limited resources, or when a specific heap size is required by the problem domain, this constraint is particularly very useful. And then we add a given element to the heap by placing it at the end of the underlying array self-heap. The self-real size variable keeps track of the current number of the elements in the heap, since the array indices in Python start at 0. So by using the self.heap as self.realSize, we are adding the new element at the next available position in the array. And then we assign the index of the newly added element into the underlying array self-heap into the variable index in the previous step. Since the element was added to the end of the array, its index is equal to the current number of the element in the heap, which is represented by the self.realSize. So in this heap's underlying array self-heap, we try to calculate the index of the parent node of the newly added element. The heap is represented as a complete binary tree, which is by using an array with the root node which is stored at index 1, which leaving the index 0 is unused. So the parent node index is node index 4 divided by 2, and the left child node index is the node index multiplied by 2, and the right child node index is the node index multiplied by 2 plus 1. And then, after we added a new element to the heap, we have to restore the heap property. We just repeatedly comparing the value of the newly added element with its parent node, and then we swap in their position if it is necessary. The while loop runs as long as these conditions are met. The first condition is if the value of the newly added element, which is at the index, is smaller than its parent node, which is at the index parent. And the second condition is if the index of the newly added element is greater than 1, so that we can ensure that it doesn't go beyond the root of the heap. So inside this while loop, we perform the following operations. First, we swap the value of the newly added element and its parent node since their positions have been swapped, and then we update the index of the newly added element to the index of its parent, and then we recalculate the index of its parent node by using the update index value, which is assigned the index floor divided by 2 to its parent. And this loop will continue until the heap property is restored and the newly added element reaches its correct position in this heap. So after we adding a new element to the heap, we have to maintain the maximum heap property. We have to check if the newly added element is greater than its parent node, and if the index of the current element is greater than 1, meaning it is not the root. So if the both conditions are met, it means the maximum heap property is violated. So if the maximum property is violated, we have to swap the current element with its parent node. So these operations moves the larger element up to the heap, which helping us to restore the maximum heap property. So after we swapping, the index of the current element is updated to the parent node's index, and the parent node's index is recalculated as index floor divided by 2. This is because the current element has moved up to the heap, and we need to continue checking and swapping with its new parent if it is necessary until the max heap property is satisfied. This loop continues until the maximum heap property is no longer violated or the current element becomes the root index as 1. So this process is also as known as the percolating up or sifting up the newly added element in the heap.